What does a software engineer need to know about characters? Before I get into the more detailed definitions, I want to start with an example of why characters are more confusing than they seem. Let's take this example with the word fiancé. So how long is this string here, fiancé? Well, I can count 1, 2, 3, 4, 5, 6 characters. And indeed, we do have 6 characters. This final character has E with the acute accent, but that's okay because in UTF-16 we can represent that in a single code unit. So how about this? How long do we think this is? Turns out this one is actually 7 characters long. And that's because instead of using a single character for the E with the acute accent, we're actually using a regular E, and we're combining it with the diacritical mark combining acute accent right there, and we combine these two to get the E. So we render it the same way. It represents the same character, but internally it's being stored as 2 different code units. And in the programming language of Java, for example, that's actually considered 2 separate characters, even though when it renders on the screen, it's only 1. So now we can see how we can actually make our string longer by using a less efficient representation, splitting the E itself from the mark. Can we go the other way? Turns out we can. This one, how long is this? This is actually of length 5. So how do we pull that off? Well, it turns out that there is a ligature for FI. So we can represent that as a single character, and then we have the IANCE, A with the accent, as regular. The last example, I'm going to go back to just a regular E instead of the E with the accent. And this I somehow managed to get 12 characters long. So that is because I'm using the mathematical alphanumeric symbols. These each take up 2 characters in UTF-16. So here we have to combine the high surrogate with the low surrogate. These are referred to as surrogate pairs in UTF-16 to combine together to get that F. Notice that if we try to render the characters individually, we can't, or the browser can't, because it doesn't know what this is. It only has half a character. There's a lot of terminology surrounding characters, and the terms are so interrelated it is hard to define them all in a non-circular manner. So I'm going to try to provide definitions that are meaningful even though some are circular. Character. For technical people, this usually refers to either a code unit or a code point. For business people, this usually refers to a grapheme or ligature. The different ways this word is used is a source of a lot of confusion, especially since it is used in the definitions of other terms. But once you know the entire vocabulary, you can usually figure out what it means from context. Grapheme. The smallest meaningful contrastive unit of a writing system. Contrastive means they are designed to be distinguished from one another. For example, a C is different than an E, yet 2 C's are the same even if they have slight differences in their shape. Examples of graphemes are alphabetic letters, Chinese characters, numbers, and punctuation marks. A glyph is the shape of a marking representing a grapheme. Different glyphs may represent the same grapheme. For example, there are many different styles an A can be written in that still represent an A. A ligature is 2 or more graphemes joined as a single glyph, such as the ASH character, AE, which looks like an A mushed up against an E. The code point represents a single character in a code space. This is a number that corresponds to a single character. Code space is a range of numerical values that have corresponding characters. A code unit is the smallest computer unit with which to build code points. In most programming languages, when you get the length of a string, you are counting the number of code units. A char set is a set of characters that can be mapped into a code space. An encoding is the rules for converting between code units and characters in a char set. If the size of a code unit can be different from the size of a code point, this will involve converting between code units and code points as well. A font is a set of glyphs with a particular set of parameters, such as weight, slope, width, serif, monospaced, etc. A font family, also known as a typeface, is a range of fonts that share an overall design. Common font families are Helvetica, Arial, Times New Roman, and Courier. Unicode is a standard whose goal is to unify all languages by providing a consistent way to encode text. This means assigning a number to every grapheme, ligature, accent, punctuation mark, and so on. Even some obscure alphabets that are no longer used are included. For some of these alphabets, we don't even have complete information about the meaning of the letters, such as the alphabetical order. Emoji support was added as of Unicode 6.0. UTF, Unicode Transformation Format. It refers to a set of encodings that support all Unicode code points. UTF-8, a variable length mapping between 8-bit code units and Unicode code points, where each code point may be represented as between 1 and 6 code units. UTF-8 is designed to be compatible with ASCII. Currently, no Unicode code point requires more than 4 UTF-8 code units. UTF-16. Originally intended to be a fixed-length mapping, it is now a variable-length mapping between 16-bit code units and Unicode code points. That UTF-16 is such a common representation in so many languages is unfortunate. UTF-16 has the disadvantage of taking more space than UTF-8 for the most common characters, with none of the advantages that would have come with being a fixed-length encoding. So between UTF-8, variable but concise, and UTF-32, fixed but taking up much more space, we have the worst of both worlds. Byte order mark. A sequence of bytes placed at the beginning of a file or character stream used to designate byte order. This is skipped over and not considered a character, as it is metadata indicating whether or not bytes should be reversed before being encoded into characters. In UTF-16, it is FEFF. When consuming bytes, if they were read as FEFF, then we know the stream is big endian. If they are read as FFFE, then we know the stream is little endian. In UTF-8, there is an optional byte order mark of EFBBBF. It has no meaning and should be discarded upon being read. If you don't account for the possibility of a byte order mark existing, this can lead to some confusing behavior in your program. ASCII, American Standard Code for Information Interchange, includes the characters Americans are most familiar with. ISO-8859-1. This is a character encoding with support for languages used in the Americas, Western Europe, Oceania, and much of Africa. It is noteworthy because it is the default encoding of HTTP content. Serif, a small line attached to the end of glyphs. Sans serif just means no serifs. It is easier to illustrate the difference between serif and sans serif by example. A serif is a small line attached to the end of a letter or symbol. So if you look really closely here, you can see at the bottom of this F, you have these small lines coming out to either end. Same with the H. Also on the Z up here, you see this little line coming down, this little line coming up. You look at those same letters in a sans serif, or no serif font, we see we've got none of those little lines here. You look at the Z, it just doesn't have anything, it just ends. A bit easier to see in the capital letters, and also even in the numbers you have this, like see on this 7, you have this little line coming down. So that's the difference between serif and sans serif. Sans serif just means without serif. So how does this affect the way I code? Considering the following Java code. Here we are constructing a file reader with a file name. In Java, the reader classes read characters, not bytes. It is not possible to convert from bytes to characters or characters to bytes without knowing the encoding. If you remember nothing else about characters in software engineering, remember this. It is not possible to convert from bytes to characters or characters to bytes without knowing the encoding. So how exactly do we know what encoding we are dealing with? You don't see it specified here, so something else must be happening. What is happening is that the file reader is choosing a default encoding based on the platform on which Java is currently running. This necessarily means this code is platform dependent. It is not guaranteed to do the same thing if run elsewhere. If you do some digging into the Java library source code, you'll find the code is doing something similar to this. Here we create a file input stream, which reads bytes, and then we wrap it with an input stream reader, giving it the default char set. So now we know what char set we're dealing with. We can convert bytes to characters. So now the previously hidden input to the function is revealed. This default char set right here. In general, you should be specific about what encoding you are using, so instead of going with a default encoding, do something like this. Here we have the same thing, but instead of going with the default char set, which is again making us platform dependent, we just choose specifically what char set we have. There's a standard char sets class in Java, which has a bunch of char sets to choose from, or a bunch of encodings. They call it char sets. So this example illustrates two mistakes in the Java libraries. One mistake is that the file reader does not take an encoding, even though it absolutely needs one to convert bytes to characters. This constructor should not even exist, this constructor right here with the file reader taking a single string and not taking an encoding. And instead there should be a constructor that takes an encoding, which unfortunately for file reader does not exist. Another mistake is the use of the word char set in here and here, where encoding is what really is meant by this. For example, UTF-8 and UTF-16 have the same char set. All the characters in UTF-8 are also in UTF-16, all the characters in UTF-16 are also in UTF-8. But they have different encodings, meaning the bytes are constructed differently. Another situation that turns out to be more complicated than it first may seem is HTML documents. For HTML documents, the encoding is specified in the charset meta element like so. Here we have the meta element with name charset and value UTF-8. Given that it is bytes, not characters, that are transmitted over the Internet Protocol, can you see the problem with this? Pause the video, think about it, and then resume when you have your answer. Welcome back. The problem is that to get the encoding, we need to convert bytes to characters. But to convert bytes to characters, we need the encoding. So how does HTML5 deal with this? Well, from the HTML5 specification, the character encoding declaration must be serialized within the first 1024 bytes of the document, and it must be in ASCII. So this can cause some unusual problems or unexpected problems when you are using an encoding not compatible with ASCII. So an ASCII incompatible encoding would be one where the characters in this range don't actually map to the same characters in the Unicode code space. What this distills down to is that in order to ensure you can reliably interpret the characters in an HTML document, you need to do two things. You need to make sure that the encoding is specified within the first 1024 bytes of the HTML document, and you need to make sure all of the bytes encountered before the charset meta tag are compatible with ASCII. To give you a more concrete example of how character encoding works, I'm going to demonstrate how to take the musical symbol Gclef and convert it from its encoded UTF-8 bytes to its index in the Unicode code space. Here you can see its UTF-8 bytes are F0, 9D, 84, 9E, and its index in the Unicode code space is 1F3BC. Here I have listed the UTF-8 encoded bytes for the character in hex, and then we're working towards the Unicode code point, also listed here in hex. This is a handy table for converting between decimal, hex, and binary. So again, the UTF-8 encoded F09D849E. This is the binary representation, and we're working towards the hex, or the Unicode code point of 0001D11E, and again, here's the binary representation. So how do we make sense of all this? Well, the way UTF-8 works is that if the first bit is a 0, we know that our character is only 1 byte long. If the first bit is a 1, then we start looking to see how many 1s we have, and that tells us how many bytes we are long. So in this case, we have 1, 1 before we hit the 0, so that means we're 2 bytes long. In this case, it's 1, 1, 1 before we hit the 0. Now we know we're 3 bytes long, and so on 4, 5, and 6. So what if we see a 1, 0? Well, that would indicate we're 1 byte long, but we already covered that in this case. That's 1 byte long. So if we see a 1, 0, what we know is that we're in the middle of a Unicode, of a UTF-8 encoded character. So if your stream started in the middle of a UTF-8 encoded character, it knows that it doesn't have enough information to interpret that. So what will usually happen is they'll just keep scanning, throw that away, and keep scanning until they get a character that is at the beginning, either starting with a 0 or a 1, 1. So here I have the UTF-8 hex characters. so F09D849E, and the corresponding binary for that, UTF-8. And so you see the F goes to all ones. We can tell that from my chart up here. F is all ones. 9D849E. So first thing we do is we start looking at this first character, and we see it starts with a 1, 1. So that means this is a multi-byte character. So how many bytes long is it? Well, it's 1, 2, 3, 4. There's 4 ones there until we hit the 0. So now we know we're 4 bytes long. And now we know the next 3 bytes are actually part of the Unicode code point, which is 000. So we just pull down those, and then these we throw away because they're not significant. They're just part of the structure of the UTF-8 encoding. So next up, we have something that starts with 1, 0, so that tells us we're in the middle of a character, which is exactly what we expect, because we know from here we have 4 characters. So we throw away those 2, and we just pull the rest down. So here we have 0, 1, 1, 0, 1, or 0, 1, 1, 1, 0, 1. Next character, again, starts with the 1, 0, middle of a character, as we expected. Take the rest and pull them down. So again, if you look up here, these are the significant bits. And finally, our 4th character, again, starts with 1, 0, so we know to pull these bits down. So next we take all the significant bits, we smush them together, and then we break them off 8 bits at a time. And now, so I take the first 4 characters that's 1, 1, 1, 0. So looking up at my chart, what's a 1, 1, 1, 0? That's an E in hex. So I write down E. Then we have 0, 0, 0, 1, which is a 1. Again, another 1. And then 1, 1, 0, 1. Let's go look up at our chart. 1, 1, 0, 1. That's a D. So we write down the D. And then another 1. So this is how we convert the UTF-8 encoded character to its corresponding code point in Unicode.